So hi there, Lee Polite again from Axion Labs, and today we're going to talk about instrumentation for HPLC, and I'm going to take you on a tour through a typical HPLC instrument. So a couple of comments. First statement, there's a lot of different vendors out there that make HPLCs. There's a lot of great ones out there. The way I always approach HPLC is HPLC is HPLC. It doesn't matter what brand you have. You need to choose the right flow rate, the right temperature, the right solvent strength, the right particle size. That's independent of the instrument. So to me, all instruments are the same. Of course, my friends at each of the companies would disagree with that statement, but all instruments are the same. They're all good. They all do what we want them to do. So let me take you on a tour through a typical instrument. This is an Agilent 1200 SL. Not their latest instrument, not their oldest instrument, but somewhere in between, a very popular model. So what we have at the top is we have our bottles of mobile phase, water and methanol. We're going to blend these two to give us the correct strength in order to get the right separation. So that is a critical piece of chromatography. Notice water we usually put in a brown bottle. That's to prevent microbial growth. We don't want algae growing in our water bottle. Notice something else if you look at my label. I actually put a little bit of methanol in my water. That's a trick that I've learned over the years, and that is it keeps microbial growth under control. In the olden days, we used to use sodium azide, which kills everything. And after doing that for 20 years, people started saying, it kills everything, huh? Wonder what it does to humans. So maybe that's not good for humans. But methanol, 5% methanol in the water bottle seems to keep it good for, I would say, for at least a month at a time. I also use phosphoric acid in my water. We could talk about that in depth when you come to the class. The other bottle, the B bottle, is methanol. That could be acetonitrile. Those are the two most popular. So if we sort of go down this stack, the next piece we have is the degasser. So an online vacuum degasser will remove dissolved gases from the mobile phase. So first question, why do we care about that? Well, when you mix methanol and water, you will get bubbles. It's because at room temperature, room pressure, we have gases dissolved in these liquids. So oxygen, nitrogen, carbon dioxide is dissolved. When we put that under pressure, it's not a problem, but when we reduce the pressure, when we put a vacuum on it, we actually cause that bubble to come out of solution. So the way I put it is, how does a pump work? Well, a pump needs to suck in that solvent. By sucking in the solvent, it will cause bubbles to form, and those bubbles will drive your pump nuts. No HPLC pump in the world does well with bubbles running through it. So step number one, let's get rid of the bubbles at the source. So what we do is we take the water and the methanol, we send it into a vacuum chamber, and it goes through a semi-permeable membrane. It's Nafion, like a porous Teflon. And as it goes through this membrane, the membrane is sitting in a vacuum chamber, and all the gases come out of solution as bubbles. Those bubbles pass right through the membrane, and they get pumped out to waste. Liquids cannot get through the membrane. So by the end of this piece of tubing, we have pure liquid, pure water, pure methanol, no bubbles at all. That is going to make the pump much happier and ultimately make the detector happier. We're going to get lower noise in the detector. So degasser is one of those things that we just always use it. You plug it in, turn it on, it always works. In the olden days, we had to degas offline using helium or using an offline vacuum. You do not need to do that anymore if you have a vacuum degasser. I do have some customers who will come in and who will do both. You can do that if you want, but I promise you, you're wasting time. The vacuum degasser is much more efficient than the other approaches. So this produces nice pure liquids coming into the pump. This pump design is called a binary pump or a high pressure gradient pump. This is one of the more complicated designs out there. The other design is what's called a coronary pump. We'll just have one pump head. But let me use this one for an example. The two pump heads, two pumps. One pumps pure water. So pump A is pumping pure water. Pump B is pumping pure methanol. Now, of course, I want to blend the two. So I tell the computer I want to blend, let's say 50-50. So what it will do is, if I want to run 1 milliminute 50-50 methanol water, it'll set pump A for half a milliminute, pump B for half a milliminute, and then the outputs come together, this little piece right there, and they combine, they mix. So coming out of the pump, I will then have 50-50 methanol water. So this is what determines the flow rate, right? Little pistons moving back and forth. And it also determines the composition, the percent methanol, the percent water. Both of those are critical. So now the output of the pump is coming out in this tiny little piece of stainless steel tubing. Remember, low pressure liquid goes into the pump, high pressure liquid comes out. This pump will go up to 9,000 psi, that's 600 bar. So through this little piece of tubing, I will have a very high pressure liquid. The next step is the auto sampler. We need to pick up our sample. So if you look at the auto sampler, we have a bunch of vials in here, and what will happen is with this design, the needle will simply pick up from its home position, it will move to the correct vial, stick the needle into the vial, and then we have essentially a syringe, what Agilent calls a metering device, but I call it a syringe, and it's going to pull in the correct amount of sample. So this has a digital stepping motor on it. It knows how many clicks it needs to pull back to pull in your 5 microliter or your 10 microliter injection. So the sample is going to be contained inside this needle right here. And then when we make the injection, what we do is we really just take the flow and send it through the needle. So the flow is going to come through this, grab the sample, and then the next step is going to be the separation. So that's the column. So the column compartment, this is a heated section, or cooled. This is a Peltier device, can heat or cool the column. In general, in HPLC, we want to run at constant temperature. So choose a temperature, set it, leave alone, don't ever touch it again. Temperature is important that it's consistent, but in my opinion, not that important what it is. So if you want to make your life easy, I run everything at 40 degrees. Every sample I've ever run, well, most samples I've ever run, I run at 40 degrees C. It works well for HPLC. Slightly elevated temperature makes the pump happier, lower viscosity. A lot of reasons why we like slightly elevated temperatures. 40 degrees pretty much does it. Do not go above 60 unless you have to. Above 60, we start to damage the column. Low temperature, we can go down 10 degrees below ambient. For chiral separations, I will use subambient temperatures of 10 degrees for separations. So this is the Peltier block. There's actually 2 of them. We could control 2 different temperatures. I have no idea why you would want to, but we do have 2 blocks. Usually we tie the 2 together in the software and they're set at the same temperature. Columns. This is a traditional column, 25 centimeter, 5 micron. This is what most people buy. This is the most common column dimension bought. Now I'm here to tell you that this is horribly old-fashioned. If you're buying this column, stop buying it. I didn't mean the brand. If you're buying a 25 centimeter column, there's better ways to do things today. So I'm a big fan of short columns. So this is the column that we're actually using. This column is 5 centimeters long. It contains 1.8 micron particles. Just to put this in perspective, this column is 5 times shorter than this column, which means it's 5 times faster. 25-minute run, 5-minute run. 5-minute analysis, 1-minute analysis. Now in terms of the quality of the analysis, you're thinking longer is better. Well, not necessarily. This has a certain amount of efficiency. A column like this has about, I'm going to ballpark this, about 20,000 theoretical plates. A column like this has about 14,000 theoretical plates. So it's nearly as efficient as a really long column, yet it's 5 times faster. So a lot of applications do not need the brute force of a long column, can be much better done on small columns with small particles. I'm a big fan of that. Everything is faster when you get to this. So notice that the fitting going into the column, that's a high pressure fitting. Remember, this is a 9,000 psi instrument. All the pressure is really going to be right there. After the column, there's not much pressure. Maybe 100 psi left because there's not much to go through. So this is the critical piece. We want to make sure it's a really good fitting. Lots of different fittings out there. We have permanent fittings, stainless steel fittings. We have plastic finger tights, which I like. This one on the top of the column is one of the newer fittings out there. A bunch of companies have gotten into this, and that is finger tight fittings for high pressure. This one is one of my favorites because it's finger tight. So you simply, I'll show you how it works. So you take this and you can stick it into any column, and you tighten the little blue knob there. And once you just get it finger tight, the last step is to push down the lever, and that lever takes you up to 20,000 psi. So I can finger tight it. I don't need a wrench. Again, this one's made by Agilent. Great fitting. They're out there. Other people are making them similar types of fittings as well. So big fan of universal fittings, and watch the high pressure part of the instrument, because this is, again, this is where most of your pressure is. Coming off the column, the last piece is the detector. So the column has produced this beautiful separation. Remember, that's the heart of the system. everything, all the magic is happening here. Once we've separated, the next step is to detect. So the detector, this is a UV detector, it's a diode array detector. Let me show you the functional part. Down here is the flow cell. So it's really what I call a block or a cylinder of stainless steel. We drill a hole through the middle, and we put a quartz window on each side. So the flow comes down this way, goes down the length, and then goes out. We call that a Z flow cell. And then we shine really bright light in here, and we measure how much light makes it to the other side. So if something in my sample absorbs light, then the intensity is going to drop. So instead of measuring intensity, we measure absorbance, flip that around. So we get no absorbance until a molecule comes through the detector, and then we get absorbance. So we have a really bright light, a deuterium lamp on the left side. We also have a second lamp, a tungsten lamp for visible. And then on the right side, we have our diode array. We have our detector, the thing that's actually counting the photons coming off of it. As an added bonus, the diode array gives us the entire UV spectrum continuously throughout the run, so we can do some neat three-dimensional stuff as well. So this guy fits back in there, snaps in. So that's a tour of the instrument. I guess the last thing I didn't show you was a waste bottle. Well, you'll figure that part out. So HPLC is fairly straightforward, a bunch of simple things hooked together to make something that looks complicated.